Yep. 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 Ooh wee! Is it really about that time? I think it is. I really do think it is. Guess what? It's just about that time. Mm-mm-mm. Let's get this show going, eh? How about now? Thank you, Kitsune. I really appreciate it. I didn't even notice that my sound was not being outputted. Can you guys hear me now? I hope so. So I guess I'll just start back at the top. Um, we're gonna go over how do we know proofs are proofs. We wanted to go over the ledger thing, but as we keep getting the data, more stuff comes out. Again, thank you, Kitsuna, for letting me know my audio wasn't coming through. And So as the digitalization of the world occurs, more math they consider, they transfer, and they hold the secrets to basically everything and anything online. We've talked about various ways that we do proofs, various ways proofs are being used, and even how like it's used to remove the need to transfer some data or to be used with that data as like a proof check, like a check that you got it all there. And with so much of this proofs being used, especially with maths, like how do we basically prove a proof? That's really what today's about. And so I just want to point out this kind of relates back to the common question of like, how do we know maths are correct and they're not systemic lies? And under the circumstances, very recently, the past few years, I mean, this doubt is merited, and there's a good reason to want to question this. So let's change our perspective of maths and what proofs we use with maths as a being systemic truth or an unnatural truth, or to say that it's a naturally false lie, or a naturally false truth, as you kind of hear it more oftenly said. I'm going to get this back up behind me, and we're going to jump into it today. So, respectively, let's define what exactly a math is. And a lot of times people want to make this very complicated, so we're going to make this as simple as possible. Mathematics is an area of stuff that is basically containing to a few topics. As you can see here, it's really just the area of knowledge including topics of numbers, formulas, structures within those shapes and spaces. I know that sounds like a bunch, but it's basically just an additional way to measure things. That's a great way to look at it. Like, this is, math is used to measure things, and rather that's a space, a number, an amount, how many fingers are in my hands, or how far I see. It's all used in these setups. So they say modern mathematics is sets of subdisciplines: number theory, algebra, geometry, analysis, respectively. It goes on and on and on. So when we drop down what is math, it is discovering of properties of an abstract object to simply prove they exist. This is when we come across like axioms, abstractions, theorems. You come up with all these different words that just basically means like abstractions is just ideals that we have reasons to prove. Axioms are like ways we explain our proofs. Theorems are the ideals behind the proofs that are in a format that is repeatable and understandable. And so when we go to where does a lot of the math come from, it really at one point was like a language or something, but when we think of mathematics nowadays, this is what we're thinking. We're thinking of concept of proofs for associated mathematical rigor, as in like Greek mathematics, most notable as in the Euclid's Elements. And in the beginning, mathematics was divided into two main groups: geometry and arithmetic, which is manipulation of actual numbers and fractions. And you're going to see that word a lot. Like, a lot of math is technically a type of manipulation of data. And when you think about it like that, you then realize there's a reason why some people just don't trust it. It's kind of hard to believe. Some of it's real, some of it's not, and we're going to go over a lot of that. We're also going to show you how you can prove it to yourself. These things are real or not real, which is the awesome part about this, right? So basically, at the end of the 19th century, we developed a new formation of mathematics, which then breaks down to, as you see here, contemporary mathematics subject classifications, who are the first 60 levels of areas of mathematics. So basically, in my opinion, mathematics was then made extremely complicated because other areas of mathematics kind of got studied to the point where we couldn't study any further. So one of the things, key points here is that mention this etymology, which it's basically just meanings learnt and to study. So that's where we get like learnt, what one gets to know, study of a science. So mathematical study is really what it's referring to. So it's studying things. Why are my eyes keep Weird. Anyways, we can go further on to this, but that's the basic points. Okay, mathematics is manipulation of numbers, and all mathematics are built upon concepts or ideals that uses of various different things to make it understandable, but uses a proof to show its proof. Something that then you can repeat on your own in your own manner, and if you get a similar proof, then the proofs are identical. When proofs are identical, then we say, yes, this is correct. Because more than one person used more than one method to come up with the same answer for the same problem. Proofs. But it gets a little bit more complicated than that, because a mathematical proof actually is something slightly more. A mathematical proof is an integral argument for a mathematical statement. And then that is some kind of logical assumption used for the conclusion. So that's a really key point here. This means that a mathematical proof doesn't actually have to answer the correct answer. Really, it just has to explain the argument of the statement in a logical manner. Rather, some logic is assumed or some logic is real. And the argument may use other previously established statements or theorems, as in like part of its setup, but it still needs proofs for its principles or concepts or axioms or things. And a proof is going to be some form of inference, something you have to infer or figure out on your own. A lot of times they use planes of ideologies to explain concepts. And when you look at how like a lot of early math problems were solved, they were all using like visual concepts to explain themselves. And so there's a lot of proofs around visualizing the mathematical problem. And so a proposition that has not been proven is a conjecture. Instead of a hypothesis, it is frequently used as an assumption for further mathematical work. So a conjecture is like basically there's no further work really needed, and it hasn't been proven. And then while a hypothesis means that there is potentially, or there is most definitely, further mathematical work needed or possible. So basically when you're saying a conjecture, you're basically saying like, I'm proving you wrong, bro. Alright? And we're not actually saying you're proven wrong, but it's very similar to the same statement. It's kind of like when you're in the middle of making a statement and then someone come up to you and just be like, bet you wrong, here we go, let's drop it down to a song. And next thing you know, you're getting, you're hearing the 9 tells of why you were just wrong. But then they have to bring up their proofs and blah, 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 blah. So if you get that reference, then you're understanding what I'm talking about. So let's keep going. We're just basically saying proofs employ a logic system using oftentimes mathematical symbols instead of like a natural language to make it a little bit easier to write down and understand. And sometimes mathematical literature are so very rigorously in formal logic, and that can be a problem. Like it's basically saying that the symbolic language used in proofs doesn't always match up to each other from proof to proof. Sometimes they have to be re-explained mid-proof at the beginning of proofs, so you tend to have a lot of times proofs explaining what they're about to explain to explain their explanation, which is another reason why a lot of people don't believe in these things. It's starting to make sense, right? So the distinction between formal and informal proofs has led to much examination of the current historical mathematical practices, the quasi-informational mathematics, and so-called folk mathematics, other oral traditions in mainstream mathematical community or other cultures. The philosophy of mathematics is concerned with the role of language and logic and proofs mathematics as a language. And a lot of people don't understand this. Math was originally a language. We could actually originally communicate with people by holding up a 1 and a fist and putting them closer and closer together, and people would understand that the 1 was us, like the thing, right? And then the rock was the other thing, And either you pointed at each other and you put up the 1, or you didn't point at each other and you put up the rock. So either the rock represented us as a whole, or the rock represented something coming at us. And depending on, so this is all the same concept. Depending on how we set it up, depending on how we move our hands, whatever, talk, changes the whole construct of what we're really doing in a proof. Oh, math. I really am a big fan of math. Turn up the volume. Ooh, okay. I think we got a little bit more volume. Ooh. All right. So when we go down to a mathematical fallacy, this is more like what a lot of people are trying to claim nowadays. They're trying to go, nah, bro, this is just straight up fake, false. So as we see here, an invalid proof redirects here. Just realized I have not been giving you guys the QR codes. Oh no, the QR codes don't pop up anymore. That's why. I'll be honest, I've been having all sorts of problems today. So my QR codes are not popping in. My bad. I will have to get, those will be in the description later on. If they're not already in the description right now on YouTube. So, invalid proofs redirect to this mathematical fallacy Wikipedia page. And the 0 equals 1. That's a really good way to explain this. No joke. Really good way to explain this, because that is mathematical fallacy, and it is also considered a math trick. So mathematical fallacies can sometimes be proven as sooth or truthful, or a non-objectable truth that one person can experience on their own. So oftentimes these math tricks, like 1 equals 0, are not real proofs, but from the mathematical methods created to explain higher formats used on lower formats. So does this mean that fallacy is a fallacy or misuse proof? Let's look at some of these provable situations, because when we go down to math fallacy, that's actually saying something is false. But the problem is a lot of fallacies are used as proofs. And it gets to be very, very confusing. And we see here one of the very main ones, for example, is division by 0. And yeah, that 0 equals 1 was another one. But that 0 equals 1 is an entire form of mathematics, which is really weird. So earlier we saw something saying like oral mathematics and things like that. So we're going to play part of a quick clip video from Beverly Hillbillies. Oh, what?
I figure 75% to you, Pon Ma, and 25% divided between the 5 of us. Gida, Crowbar, myself, Tom, and the baby.
Pretty simple.
5% for each one of us.
Billy, you're cheating yourself. If there's 25% divided among the 5 of you, that's 14% apiece.
Oh, no, listen, Pa. I wouldn't cheat you.
They're going to show proofs now.
Look here.
Proofs.
I'll show you. Let me rub this out here. And now, 25 divided by 5 is 5. You see, 5 won't go into 2, will it?
No.
But
no.
5 goes into 25
5 times.
You see?
Oh, you're wrong, Billy. Now, I'm a pretty good mathematician.
Pretty good mathematician.
5 into 25... 5 won't go into 2, will it?
No.
But 5 goes into 5 once. Now, we didn't use the 2 before, so we bring it down here. Now, 5 into 20 goes 4 times. There you are. 5 into 25.
It gets worse. This proof can be taken down another step. Okay?
Times 14 is 25. 5 times 4 is 20. 5 times 1 is 5. 25. That's it.
But wait, we're not done. We can break this fallacy down another time.
Is not 25. 4, 8, 12, 16, 20.
21, 22, 23, 24, 25.
Now, in this point of all the phallic examples, it's pretty easy to see one thing. They're counting the tens place as a ones place. Sure, this is easy to see in this, but we needed 3 separate examples and proofs to then finally see where they were actually going wrong. And this is an important part of proofing, because we simply just can't prove something. So, discovering a fallacy is not just the only thing. Let me go to the next step. Mathematical fallacy proofs. Yes, there's entire papers on proving mathematical fallacies. Not just proving that they are fallacies, but showing the mathematical proof, proving they were provable. This is really creepy. 1 equals 0. Surely it does not, but if we take n plus 1 to the square equals n squared plus n 2n plus 1. So we expanded the equation to have then now a variable we can manipulate in. So then we take and we subtract from both sides, then we add to both sides, we factor in, we add into both sides, because we need to make sure it's symmetrical. We factor again, we take the square root of both sides, because again, we've got to make sure it's symmetrical. And we subtract from both sides again, got to make sure it's symmetrical, which is impossible at this point, leaving the last point here, 1 equals 0. So, the problem is, that proof does mathematically prove, and it does come out correct. It's still a lie. It's still false. The operation listed in the above utilizes basic arithmetic to arrive to a false conclusion. Starting by simply expanding a squared equation, we can subtract from both sides to isolate the square. Subtracting from both sides then allows you to be factored, and then adding to both sides, once again, will then allow you to factor it down from the square form. Once it's down from the square form, it is basically then subtracting blah blah to complete the proof. But if the two numbers are equal, their squares are also equal. However, the reverse from such is not. So basically, just reversing this math shows you that it's not right. 1 equals 2. Let a equal b, then a squared equals ab, a plus. So you're noticing they're over expanding. They're taking something simple and turning it complicated. They're using higher form mathematics to explain lower form mathematics. So this is a common Curie's paradox. Curie's paradox is a thing of triangles. This is Curie's paradox. These two triangles are the same size. These two triangles can contain different lengths, and depending on the situation, you can have an extra one. This is why you see some people take the candy bar, cut it at a weird angle, and then break it down into certain pieces to be able to take one piece out and give you a whole candy bar. This is what they're doing. They're taking this structure and turning it into this structure. You don't actually, like literally, this just goes down here, this goes up there. It's the same exact structure. It's just 1/10 smaller or something like that. And this was developed in 1953. And this is known as Diocles identity, which is where that thing comes from. F n times Fn minus 3 minus f to the n, one spot to the f to the n, second spot, excuse me, equals -1 to the n. And all acute angles are right angles. I mean, this is obviously not true, but this is a way to prove that it may be potential. This is a phallic proof. And we see that was made by MIT. So here we go for color theorem. I think this one right here is a little bit more, you know, read at your own risk type thing. Because, yeah, you read it and you'll see. Let's just keep going. Because basically, what is correct way of disproving a mathematical statement? Because, like I kind of hinted at earlier, we can't just say it's not there. We have to give reason. So basically, we have to know like how, why, when, what. So we can't. Let me backtrack. Not just going something is wrong. We kind of can't just say something like, here's a different way to do this for a different answer. We truly has to actually disprove it specifically, which sounds really difficult, but it is difficult. What can I say? There's no real correct way to do anything with maths. So you really have to know, you have to be able to prove what, where, how, and why with the phallic proof and phallic math, and show another way to do it, obtaining a correct answer with a proof behind why yours is correct versus theirs is wrong. So basically, to prove a proof wrong, you have to then prove every point of their proof wrong, and have another set of proofs to prove your proofs are right, which is really difficult. So, this question is motivated by a midterm exam. This is an exam where the questions is asked like this. And the following statement is true, prove it otherwise, or disprove it. If math and math are vectors in 3 dimensions, then math times math equals math times math. The times operation here means cross product. And in case you don't know what that means, it's like, it's just a form of manipulation or mathematical addition. So for this question, I actually proved that math, blah, blah, blah. So basically, math times math equals negative math times math. And so the statement is false, but my lecturer declares some marks and said that my solution is not correct. So for disproving the question, we need a counterexample. So, for example, they were able to prove their thing with proofs, but they didn't have a counterexample. Therefore, their proofs were wrong, which kind of sucks. But this right here, it's actually, let's see if I can get this. Nope, still not popping up. Dang. I will get that next time. I'll get that working. I've had all sorts of problems today. Mathematics. So this is just like an example of why something wasn't whatever. And people are kind of explaining to this person why they're wrong, which in the end, other people are basically saying, well, you're right, sure, if it's correct, it's correct, but, you know, you always opt for the short and simple demonstration. As your professor's comment, if you see his proof is incorrect because you did not provide a counterexample, then it is not correct criticism. It seems simply to imply one way to give an answer to the question by counterexample. It's kind of important here. It's like the professor is saying you're only incorrect because you have no counterexample. You have no other way to show your proving statement. And so it's like disproving this weird vector to P is the same thing as disproving this weird vector to negative potential P. If you don't have a counterexample to disprove that one proves the other, then what's the point? And that's the simplest way I can think of to explain how you have to have a counterexample with counting proofs on top of your proofs of their disprovement. A lot of word here play with the word proof, isn't there? So eventually you get into things like conjectures. Yes, we're on brilliant.org. Their wiki. It's free. As you can see, they want me to join, but I can still come and look. So they actually give some really good examples here with like Pascal's triangle. We're going to go back into reader mode. Okay, that killed it. Never mind. Actually, it's giving me all the examples much cleaner in the reader mode. So basically, there's different ways that they can visualize the mathematics, and we see this Pascal triangle conjecture and expression elements in the nth row of Pascal triangle. So basically, we can see there's an issue right there. The most sensible approach in this process would be going by row to row to see. All right, there's the error right here. Third row. Let's see, 1, 2, 3. Yep, third row. Now observe him in the clear result. So, like for example, this is the counter for this one, and this also proves this is wrong. And in case you were wondering, this is just a simple proof, commonly used. Pascal is a commonly used proof, and so is this. And so, if we keep going down, you can see it's being both, Pascal's being used again, but it's not the only way to do it. This is another common way, line to dot structuring systems. And this is when you get to like planes, dimensions, all these other different formula things, and where math starts to get confusing. But the most simplest way to explain a lot of math is done with points and lines. So 1, 0, 1, 2. And you're probably thinking, bro, that ain't right. And you're absolutely right, that ain't right. As you see here, now it gets fixed. X0, X1, X2. And now we have a better formation. So it's not just a matter of the one product, it's a matter of the two products. We're moving more than just a dot, we're moving a dot and a line. So, and then you can see here proofs to prove that statement, and then using visual aids to help formulate as in your proofing statements. So then we're using this proof to prove an actual mathematical equation, and it worked. So this is another way that these are, like the example that we have here, the Pascal triangle. This is one way that was actually used to explain a long time ago by doing this kinds of things. This is another one that we see quite often where you're visualizing a graph type ideal, and graphing becomes more important in your proofs than sometimes the actual math becomes. And you see here where they even go down to show how these things are broken down to explain information. And so a lot of bits here, but different ways to show proofs, right? And what we were just basically looking at is we were looking at a statement, which is and then a conjecture, and then a proof to prove its conjecture. So that's what we were looking at. Here are some mathematical fallacies, because basically I want to give you examples of how some of these are done. Because understanding a fallacy is actually kind of complicated, and which is why math is so wish-washy to so many people. As you can see here, we have the A plus B thing again, which is trying to prove 2 equals 1. And they go through the mathematical crap to go through it again. Over-expanding something simplified, making it really complicated to when it should have stayed simple. It's easy to have a fallacy in your statement identifying your proof as being theoretically correct, no mistakes are found, but your proof ended up with some equals that are usually unequal. For example, 2 equals 1 equals B. Example. So sometimes it's down to simple little things like this equals that, when obviously we can see it doesn't. So that's the best thing here, like to look at, is it's sometimes something really simple to prove a statement or something. Like an elephant is the same weight of a mosquito. Oh my gosh, stop texting me. Okay, sorry. I'm just now getting a bunch of messages telling me the sound wasn't running, so I guess people were messaging me, but they just now showing up. And so this person, they're not ever going to show you the real proofs for a lot of these. They're just going to show you the actual fallacy and how fallacies are used to make extreme things seem real. We kind of saw the same thing when we were seeing people compare data results, and that's kind of the point here. Is it's almost the same. Okay, so we can look at logical fallacies, and basically these are super common. All of these fallacies are super common, which makes them really easy to spot. So let's go over some common ones. The straw man fallacy, it occurs when someone oversimplifies to misrepresent or misrepresents your argument. It's like if you say something and someone was like, yo, bro, what I think you're really saying from that is, instead of just saying what you actually said from that. Bandwagon fallacy, just because a significant population of the portion believes it's true, therefore it's magically true. Like, for example, the word true just means that it's an agreed upon ideal. So, for example, there could be in the future, the truth could be the sky is purple, but everyone could go out, look up, and see the sky is not purple at any point in time. So, that's bandwagon fallacy. You tend to see, well, you know, so-and-so professor said, well, this expert over here claims. That's bandwagon fallacy. Appeal to the authority fallacy. This is when, like, you'll do something that specifically appeals to a government or a major competitor or a major entity or a major whatever, maybe a CEO or a business partner. This tends to be the thing where they say 9 out of 10 scientists agree with the money or whoever paid them. So a false dilemma fallacy is basically presenting a complex set of issues with inherently only two opposite sides. You know, basically the way the Democratic Party system works in America, you only have two sides. When we actually have more than one, we actually have like multiples. We have like 8 or 9 different parties, but you only see 2 ever fight against each other. So this is a false dilemma fallacy being used to get people to vote for one of 2 specific individuals that probably neither one of them want. The people don't really want. Hasty generalization, where basically, hey, look, everything has to be done now. You know, we only got 4 years to fix this problem before we all die, bro. Climate change. So things like that. It's where the time is super important. The slothful induction fallacy is basically the exact opposite of that, where it's like, someone's not going to do it or acknowledge it or whatever, so you're using that as like a reverse psychology method to get them to then do the thing that they don't want to do. For example, even though every project Brad has managed in the last 2 years, he's running behind schedule, I think we can chalk it up to unfortunate circumstances, not his project management skills. It's pretty simple. The person always behind, and yeah, I don't think I gotta say more. So correlation causation fallacy, where correlation causation is causation and causation is correlation. Sometimes the two don't have anything. Most times the two don't have anything to do with each other, but a lot of times one will be used for the other to get people to think they do. For example, like the amount of people dying this month has to do with COVID. That was a big one used, where if you just looked at the daily death, the average deaths per month or that month or whatever, like right now we're seeing a correlation causation fallacy with a strawman fallacy and another type of fallacy, all put it together with this, hey, the world's heating up, we're all doomed, the world's heating up, but yet summer's coming for the entire northern hemisphere. Yeah, that would make sense why the world's heating up. So, anecdotal evidence fallacy is, in place of logical evidence, they just use a fallible substitute, normally from someone's personal experience, where you see people that go, testimonials are used, or fake testimonials are used. It's the exact way to explain it. So, the Texas sharpshooter fallacy, the fallacy gets a colorful name from the anecdote about a Texan who fires his gun at a barn wall and then proceeds to paint a target around the closest cluster of bullet holes. He then points to a bullet-ridden target as evidence of his expert marksmanship. Speakers who rely on the Texas sharpshooter fallacy tend to cherry pick data clusters based on predetermined conclusions. It's like, okay, I shot this one area, I shot that thing barn a bunch of times, and out of the 100 shots, I'm going to show you my 10 best, right? Things like that. Or you specifically only show things that you knew were going to happen. For example, if you was watching a movie and you've already seen the ending, and you're like, hey bro, I bet you $10 this person dies halfway through the movie or whatever in a spot where it doesn't seem likely. Yeah, stuff like that. So middle ground fallacy. Fallacy assumes a compromise between the two extreme points of arguments. Remember earlier I was saying one of the things that people might say is, so what you're really saying is blah, 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 blah. Another one, this way people do this one is like, okay, so basically let's meet in the middle on this topic and say that blah, 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 words, 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 yellow, yellow. So that's the other one. The burden of proof fallacy. This person claims X is true, and the responsibility is to provide evidence in support of that assertion. Invalid to claim X that is true for someone else to prove that it's not true. So basically, it's like when you present something as true, you're supposed to be able to, you are supposed to prove it's true. And then if someone is presenting something isn't true, normally in that case, unless it's like mathematical, they don't actually have to prove their point. They don't have to prove that you're not true. You know, they just have to prove they are true. And that's where it comes to this point of where someone comes up and they say, this is true, but you have to prove it's true. Or false. You know, so, yeah. A lot of times, people trying to get VC money will do something like that. Yeah, prove to me that that's, like, I don't believe this is true. Well, then prove it to me. Yeah, instead of just proving to the person that it is true. Personal identity fallacy. So you can see a lot of these fallacies have weird names, and some of these are because they're from specific examples. You have a difficulty understanding how or why something is true. That doesn't automatically mean the question is false. So some people will think something is automatically false because they can't understand it. I thought I shut down the volume on that. I did. Okay, so the no true Scotsman fallacy, often used to protect assertions that rely on universal globalizations or marketers love pie. So it's basically using a generalization to make something seem true when it's obviously not going to always be true or in generally true at all. Ad hominem, this is a very common one, as it occurs when you attack someone's personally rather than their logic or the example that they're giving, or the logic of the example they're giving. The two. So, as you see, there's a load of actual types of common logical fallacies. And these common logical fallacies are definitely going to be found in maths, especially maths. Here is a list of fallacies specifically to maths. And is Wikipedia list of fallacies. And in here there are way more fallacies than listed on the other page. And they're proofs and points of reason. Because the amount of ways to fake something is greater than the amount of ways to prove something. So, I want to point out what 4/5 rule is. This is something you're going to see, oh man, something that gets seen quite often. 4/5 rule is more commonly known as the 4/5 or 80% rule, described as guidelines for a section of having rate of any race, sex, or ethnic group which is less than 4/5 rate of group highest. So basically, it's commonly used as like who you have to hire. You have to have 4/5 of a something. So where did this 4/5 rule come from? So this one right here about the hiring process, 4/5 rule, is considered to be a fallacy rule, meaning it's a rule that everyone has to apply or obliged by in America under certain circumstances, but it's a rule that's considered to be false. It's a proven fallacy. So why is it used? Well, it was used in other things. For example, this is going to be courts. Actually, this website here, for chords, circle of fifths. It really just kind of explains how fifths work and stuff. They even had this like little interactive thing. It's really neat. And it kind of shows you how everything works. Because when we're talking about in 4/5, there's certain ways to move in 4/5. There are ways things happen. As you see as we go through, the what's highlighted is what's on the scale or whatever, and we can see 4th and 5ths have two different ones. We can see how they interact. We can do all sorts of different versions, and we see how they interact. And I think that's kind of neat. It kind of helps show you something that's kind of hard to explain in a lot of cases. But here's a visual map to help show you how you move in 4/5. For example, if we're starting here at C, we can move down to E, or we can move to G. So it's like we're moving in a K cluster formation. We can start in 1, and then we can move to the nearest closest sound. For example, we could move to A on the same bar, but then that's moving down in that bar. Or we could move over to F or D. But no, we can't go to F or D or A, can we? No, we can only go to the right. So technically, you can only go to the right, or you can only go to the right and down. So if we look, C is only going to the right, and to the right and down. C is only going to the right, and to the right and up, or the left and up. This looks very confusing, but in the order of 4/5, it's still considered right and down. Technically, this is right and down, and this is right. It's just because it's on this side, it looks confusing. If we was to flip this image, it would be looking exactly like this. And that's something you have to remember when you go into these little circle graphs with 4/5. The halfway point really does change the orientation of movement, because it's basically always towards the outside or towards the middle. Now that's the easier way to explain how to move in 4/5. Here's a 4/5 fraction, because if you got kids or anything, you know. But the other thing is 4/5 can be very confusing. If we look up at this little pie graph, having 4 of those colored in makes it really easy to understand 4/5. But 80%, most people don't understand that's 4/5, or 0.8 is 4/5. Or if you mark down 1, 2, 3, 4/5. And so just the way you present the data can make it either easier to understand or more difficult. Putting up a 0.8 or an 80% maybe way more miscommunicating than a line graph or a pie graph. So we need to talk about zero ring. Zero ring is a theory where all zeros is the only thing you can use. You've probably actually seen me tweet about this stuff before. I first learned about this stuff in high school and thought it was really funny, because 0 plus 0 plus 0 plus 0 equals 1. Which doesn't make any sense, but it's ring math. So in ring math, everything is 0, everything is divided by 0, everything is of 0, so 0 is the equalization of everything. And this is a very common mathematical form used to basically prove falsities. As you can see, non-communicative algebra is where it sits most of its stuff in, and some geometric algebra. Now, when it comes to geometric algebra, this one's actually going to make any sense to anything, and it's going to be usable. That's the higher form mathematics this is used for. So, when you use it for lower form mathematics, like these things here, you tend to have some falsities. And if you see prime adix is where those falsities are going to show the highest. And the reason is because people forget to keep, we tend to keep our equations symmetrical. And when we say symmetrical, you can come in here and you can find out what they really mean, but see how it comes down to equals to 0? That's the best way to explain symmetrical. There is another tons of different ways. There's like 4 or 5 different major ways to explain symmetrical mathematics. But if you have a symmetrical equation, it's equal to 0. It's not equal to something else. It's equal to 0. You end up with your equation starting off or ending equal to 0. You always do the same thing on both sides to make sure it's equal to 0. 80-20, yeah. Is that Pareto distribution 80-20? I'm assuming for the fraction. Yeah, I do believe so. 80-20. In that case, or I forgot the other one. Yeah, 0.8. So, when we are dealing with fallacies, sometimes the way to show the fallacy is to not keep the math symmetrical. So here is a fun little thing on IPFS. We're going to have the little link down below so you can get that full IPFS hashing, bring it in and run it local if you want. But this is going to allow us to type in information and it's going to give us an output. This is using 4/5 trick to deceive us a little bit. And it's not, as odd as it is, this formation is not deceiving. This is actually a way to determine if the thing that we're getting as in a string of characters length is the correct length of string of characters. That's all we're actually doing here. This was used to determine, well, not this one specifically, this form of mathematic, was used to determine if information we were getting back from the space was the proper length. Okay, am I cutting this packet too short? Is this the actual length of the packet? What's a way to figure that out? Take 1/5 of it and use the 4/5 trick to see if it's 1. Well, most commonly, 4/5 trick is, well, take 1, the 1 you got, and you multiply it by 5. If it equals up to a whole number, it's correct. If it's not a whole number, it's incorrect. But that's not the actual 4/5 trick. If we click here to learn more, and hope it pops up, yay. We can actually come down and find the math equation. 4/5 trick is the fifth, or the object, yeah, the fifth divided by 5, divided by 5. So it's the fifth of the number divided by 5, and it's the sum of that divided by the sum of that, and then the sum of that is divided by the sum of that, and that gives us an extremely large decimal, or fraction, which then we exponentially magnify that number by the remainder, and its length place. So if the remainder was 6, its length place would be tenths, or 1, or the tenths, or once. So for in this example, let's take the signature underscore 3D, it comes out to 45, 45, 51, 68. We're actually taking AC and turning it into decimal. So there's the math trick done here. This is where the trick is actually done. That if we was to use the common way to do a 4/5, where we take the 1/5 and just multiply it by 5, it would come out potentially a whole number, even though it shouldn't. So if we move the spacing, we end up with 45,455,168. We then divide that by 5, we get 9091033.6. So then we take 9091033, and we do the 4/5 trick with all that division. And then we take that, and we simply do the remainder by its place, which is 6 times 10, or 6 times 1. The great thing about the 4/5 trick is you do it to 2 different positions in its placement. So you see here we have the 1 and the 10. If 2 simultaneous, 2 in a row equal 1, then it is the first one. So this one equals 1, which it does. And this one equals 1, which it does. Which means it is the first one. It means it is actually in the ones place, which is technically the tenths place, which is correct. So this kind of explains more of what this 4/5 trick really is all about, but that's just the math. Because when we are really thinking about this, what I'm showing you here with this 4/5 trick is basically proving that we can't always use arithmetic and algebra together. And arithmetic is a mathematical operation concerned with simply numbers and their operations, while algebra goes beyond just numbers and just their operations. That really is the difference. And that is why proofs are very difficult to explain. And in the end of the day, when we're talking about, proofs of this or proofs of that, I think it's important to try to remember that, we need to prove these proofs. We can't just take a proof front value. We have to prove it. And that's the point of a lot of what we do in cryptocurrency, cryptography, cryptography, everything crypto. Because it's about the total, not about the front, not about the face. It's about what's inside of it, or not even what's always inside of it, what created it. And that's kind of the point, is when you're doing something digitally, there's an intent, there's a reason, and there's a proof. If the intent, reason, and proof all don't align, then something's wrong. If the intent aligns with the other two, and the proof is provable and also provably correct, and then the use is logical and aligns with the first one, and then it's provably correct. Even if it's something as weird as purple is not a flavor. Yeah. And I really hope you guys enjoyed today's episode, because what you thought was a proof, you now realize is actually a complicated set of proofs to just be one provable proof for you mathematically. Alright, everybody. You all enjoy your day, and I hope you guys enjoyed today. Ooh, hold on. Wait a minute. Wait. Why didn't it pop up? Give me 10 more seconds. Hold on. Let me try that again. Let me try that one more time. Alright. Hold on. I just realized what's going on. I'm on the wrong key. Okay. I hope you guys enjoy your day, and I hope you guys have a great day.